Hello, I am Mihaela van der Schaar, and it is my great pleasure to welcome you to our tutorial at ICML 2021 on synthetic healthcare data generation and assessment, challenges, methods, and impact on machine learning. It is my great pleasure to give this tutorial together with my postdoc, Dr. Ahmed Alaa. I strongly believe that machine learning can catalyze a complete transformation in healthcare by improving clinical practice and clinical workflows, empowering patients, enhancing drug development, and enabling numerous discoveries in medicine. However, all of this will not be possible without the availability of high-quality healthcare data resources, electronic health records, biobanks, disease registries, etc. However, currently, healthcare data is not easily accessible. This is due to strict regulations for data access, which are the result of perfectly valid concerns regarding the privacy of such sensitive healthcare data. Hence, the data holders cannot directly share their data with the machine learning community. And this is due to strong regulations such as HIPAA or GDPR regulations. And it is this lack of high-quality healthcare data that impedes machine learning research in healthcare. The history of machine learning has taught us that in order to make significant progress in machine learning, we need open access to high-quality data sets. And indeed, the progress in natural language processing has been due to high-quality data sets, such as WordNet. And the progress in imaging and computer vision would not have been possible without ImageNet. More generally, the current artificial intelligence boom that is enabled by deep learning would not have been possible without high-quality, diverse data sets. The story is even more complex for healthcare data. Unlike in ImageNet, where we can always go and collect additional data, for instance, a new type of car or a cat in a different pose, whenever we would like to deal with a new setting. Clinical data is about people and their health. So we cannot just go and collect more data whenever we want. There are ethical considerations we need to take into account. And also it may be that this rare disease does not enable us to just go and collect yet another patient that has this particular disease at this particular progression stage. Also, in healthcare, one data set is not enough because medicine is complex. We have many diseases, and they are very different in the way in which they evolve over time. Also, diseases may interact with each other as patients have morbidities and comorbidities. We need to learn from different types of data: images, genetic data, tabular data, event data, a diverse set of longitudinal and time series data sets. We also need to learn from diverse populations of patients that have different types of genetic characteristics, different ethnicity, or socioeconomic factors, and also populations that have been treated in different healthcare systems with different resources. Also, healthcare data needs to be acquired for different uses to empower patients, clinicians, medical researchers. Also, patient characteristics and treatments change and evolve over time. For instance, different types of populations with different types of morbidities, of comorbidities, are evolving over the years. Also, medicine is not static. It is improving. New drugs and efficacy of drugs are changing over time. There are a few laudable initiatives in sharing high-quality healthcare data. The MIMIC dataset is one such example. And indeed, a large number of papers published in ICML 2021 that are dedicated to healthcare make use of this high-quality data set. However, the mimic data set is limited in its use because it is a healthcare data set collected in United States and only for at one particular hospital and for one particular setting, healthcare setting, the ICU setting. As I mentioned, we need much more diverse and complex data sets in order to learn effectively. Also, unfortunately, companies and organizations are at times trying to lock up access to data to productize their own models, which may be suboptimal. In order to catalyze a transformation in healthcare using machine learning, we need to build the best possible machine learning models for healthcare. And this is not possible without access, open access to high quality, diverse healthcare data sets. One way in which healthcare data has been shared with researchers so far has been by using de-identified or anonymized data. And this is real data with all personal identifiers removed and data fields scrambled. However, such de-identified anonymized data has its limitations. One of them is the fact that such data is often not private. And there have been reported in recent years numerous privacy breaches and re-anonymization being possible on such de-identified datasets. There are also other limitations of such de-identified anonymized data for healthcare, and I will mention them a little later. As an alternative, we propose to use synthetic data, which is data created from scratch, which cannot be synced back to any individual if modeled properly. And this requires new methods to develop such synthetic data, new machine learning models and statistical models. So in this tutorial, we are going to discuss how we can generate synthetic data to be used for machine learning modeling, which in itself is a machine learning problem. So we are going to introduce in this tutorial a new class of machine learning methods that are dedicated to generating high-quality synthetic data. Our focus and the examples we are going to use come from healthcare. However, the vast majority of the tutorial can be also applied to generate synthetic data in other sensitive domains where sharing data is difficult, such as education, finance, criminal justice, etc. So how can synthetic data help? By sharing a synthetic proximal version of the data that resembles real data but contains no real samples for any specific individual, thereby fulfilling regulatory constraints in terms of the privacy of this data. In this way, the data holders can generate high-quality synthetic data to share with the machine learning community to generate machine learning models, which can then be used by the original data holders. So what are the uses of synthetic data? One of them is use synthetic data to develop high-quality analytics, both predictive analytics, causal inference, as well as other technologies, which can be trained on the synthetic data and then deployed on the real data. Synthetic data can also be used to facilitate the reproducibility of clinical studies and analysis. Indeed, a large number of such studies and analyses cannot be reproduced by a reader because the data that was used in these studies, it is not made public by the researchers. So it is very difficult for the community to reproduce these results and build on top of them because they do not have access to the data on which these studies and methods have been designed. Yet another use of synthetic data is to augment small sample data sets. For instance, in the case of rare diseases or for data for underrepresentative patient subgroups. And this is important in order to guard against model bias. I'd like to note here that while we can use synthetic data to augment such small sample data sets, this is not possible using de-identified or anonymized data. Using synthetic data, we can also increase the robustness, adaptability, and generalizability of machine learning models. For instance, we can transfer machine learning models from one domain and one environment to another. For instance, from one hospital in one particular country to another hospital in another country, where the population is different and possibly the type of data characteristics is different. We can use synthetic data to enable such generalization. Synthetic data can also be used to simulate forward-looking data. And this is especially important in settings such as this pandemic, where we see that, for instance, at the beginning of the pandemic, the type of population that was affected is different than now, when a certain population, older population, for instance, has been vaccinated, and the pandemic is affecting a younger population with different characteristics. Also, the treatments used in dealing with this pandemic have changed. So in order to be able to make predictions in the future, we need to simulate forward-looking data using synthetic data. Both robustness and adaptability of machine learning models, as well as the ability to train models using forward-looking data, is not possible based on anonymized and de-identified data. However, it is possible based on synthetic data. And indeed, there have been some recent successes of using synthetic clinical data in action. For instance, in biomedical imaging, where generative adversarial networks, GANs, have been used to synthesize a variety of medical images. And classifiers have been trained on real plus synthetic data to improve the predictions of rare diseases, such as, for instance, in this case, a rare subtype of renal cell carcinoma. And what's interesting is that even though the researchers had access to the real data, synthetic data was used to augment the training data and achieved improved performance. Also on COVID-19, where a synthetic data generation platform was used to accelerate the time to insight for COVID-19. However, I would like to put here a word of caution. One is to be very careful how one generates such synthetic data and gets insights for complex diseases that are evolving over time, such as COVID-19. And the metrics of performance that assess both the fidelity as well as the privacy of such synthetic data are key. Privacy concerns are especially central to any clinical data sharing, and irresponsible sharing of clinical data can lead to legal consequences for researchers and undesirable privacy breaches for patients. So we need to develop synthetic data generation that is mindful of such privacy concerns and privacy regulations. In order to explore the machine learning models that can generate synthetic clinical data, we have run at NeurIPS 2020 a competition that we call the hide and seek competition. If you want to read more and learn more about the lessons learned in running this hide and seek synthetic data generation competition, please take a look at our website dedicated to this competition. And also we have a variety of publications in the archive and elsewhere that outline the design of this challenging competition. We have organized this competition with support from Amsterdam University Medical Center, who has graciously provided us with a high-quality ICU dataset that we have used for synthetic data generation, and Microsoft Research Cambridge, who provide us with computational resources. The competition was called hide and seek because the competitors were either hiders who were aiming to design a model for generating high-quality synthetic ICU data on the basis of the real Amsterdam University Medical Center data, and seekers who were aiming to re-identify patients in the original dataset from the generated synthetic data by the hiders. Again, if you like to hear more and see more about this, please take a look at our website. But there were several key lessons learned that we are going to outline and highlight in this tutorial. One of the most important ones was that we need to carefully define the metrics for evaluation of the synthetic data, both in terms of quality as well as privacy. And if you would like to hear more about the findings of this competition, you can either watch the NeurIPS 2020 session, or you can look on our website where we have an engagement session dedicated to machine learning for healthcare that we call Inspiration Exchange, and where in February 2021, we discussed the synthetic data competition. Please take a look at this YouTube video of our engagement session. In this tutorial, as I mentioned before, we are going to introduce this new branch of machine learning dedicated to synthetic data generation. So the focus will be to generate synthetic data to be used for machine learning models, which in itself is a new strand of machine learning. We will especially try to focus on two key questions: how to build a machine learning model to generate high fidelity and private synthetic data, and how to evaluate the quality and privacy of such data sets generated by such synthetic data models. If we are able to do that, we can achieve the transformation in healthcare using machine learning that I mentioned before, because then the data guardians can provide a wealth of data, healthcare data resources to machine learning researchers and other types of data science researchers. So we can create a clearinghouse of numerous synthetic data sets that fulfill high quality and privacy characteristics. And then these data sets can be provided to the machine learning researchers to develop new healthcare tools that can enable drug discovery. We can run competition, develop models that can empower patients, do statistical research, or even build new models for insurance. These models can then be provided back to the data guardians to run on real data. If you want to read more about this vision and what synthetic data can do to empower this transformation in healthcare, please take a look at this blog on our website.
So as Mihaela explained in the introduction, creating synthetic data for healthcare applications, or creating synthetic data in general for the use of machine learning models, is itself a machine learning problem. So in this part of the tutorial, we'll be talking about the different tools that we can use in order to generate synthetic data. And we provide a non-exhaustive list of these tools. Each of these tools deserves actually a tutorial of their own. We just provide a high-level explanation on how they differ conceptually. So from a technical point of view, generating a synthetic data set means that we want to learn statistical patterns that are clinically meaningful or clinically relevant for our analysis. And we want to sample data points that mimic these statistical patterns without really having to violate the privacy of any specific patients who participated in the collection of the real data sets. The class of models that are normally used to learn data distributions instead of making predictions are called generative modeling, as I'm sure many of you are aware of. And so the first part of this tutorial will be focused on different classes of generative models and different philosophies for generative modeling, and how we can use these, or how can we adapt these to our healthcare application. The second technical issue that we stumble upon when we are dealing with synthetic data generation is privacy requirements. How do we define privacy, and how we ensure that these privacy requirements that we define are preserved in the synthetic data sets that we generate. So we'll start with generative modeling. So what is a generative model? So the generative model will be the key engine that we use to generate a synthetic data set. So if you are a data scientist working in a hospital, if you are a machine learning researcher who wants to acquire a data set held by a hospital, you would use a generative model to create a synthetic replica of this data if it's impossible to share the real data, or if sharing the real data is a hurdle. So a generative model is the key engine for generating synthetic data, and what it is, it's really a model that simulates data. It doesn't really make predictions. It's not like a supervised learning model that we are familiar with. It's not a classification model. It's not a regression model. It's really a model that estimates distributions. So it's an estimate of a data distribution that we can sample from, that we can simulate the patient data from. And by definition, it's an unsupervised learning paradigm, because we don't have inputs and outputs. We don't have targets and features. We just have data points, and we're trying to learn that are unlabeled, and we are trying to learn these distributions. The data points can also be labeled. So you may have clinical variables and clinical outcomes, but you are not trying to map the inputs to the labels. You're not trying to map the clinical features to the clinical outcomes. You're trying to simulate the whole thing. So it's considered an unsupervised learning approach. So how does it differ from discriminative modeling, which is the kind of the mainstream kind of machine learning models that we are familiar with, the supervised learning models? The difference is that while a discriminative model really learns a function, it learns how to map X to Y. Basically, it learns the conditional expectation of Y given X. The generative model learns the entire distribution of X. So if you have 100 features and let's say one target variable, 100 biomarkers, or like 100 different clinical variables, and mortality data as the labels, and you want to generate a synthetic data set that replicates this data, you would want to model the distribution of 101 variables. And you can have very high dimensional distribution. That's really what's challenging in generative modeling. In discriminative modeling, if you are given the actual real data and you have clinical inputs, like 100 clinical variables and a target variable like mortality data, you would normally want to learn a predictive model that maps these inputs to this output. So that's the key difference between these two approaches. And in statistics, this is like the density estimation problem and the regression problem. That's the difference between the two classes of models. So generative modeling is definitely a very general problem. It's prevalent in different application domains. It's not just interesting in medicine. So what makes synthetic data generation in medicine different, or what makes clinical data different? Of course, the privacy concerns that we mentioned in the beginning, but the data itself can be very complex, can be multimodal, can have diverse data structures, and we can also have domain knowledge. So the data needs to make clinical sense, and we may have prior constraints or conditions that need to be satisfied in the data for it to make clinical sense. So we can have clinical variables like a very simple tabular data set where you have like age, gender, treatment administrations, pre-existing conditions, biomarkers, and then you have some target variable, maybe mortality, maybe onset of chronic disease. That's a very simple data set. You can model this with some vanilla generative model or even some parametric distribution. But medical data can get messy. So we can have genetic data, we can have electronic health records where we have irregularly spaced observations over time, asynchronous time series, missing data, mislabeled data. The time series itself can contain multimodal data like imaging collected at some point of time, clinical biomarkers are collected at some point of time, patient goes to the hospital, then we have high frequency ICU data that's measured every few hours. So clinical data has a very idiosyncratic structure, and it can be very complex, and there is domain knowledge that can be induced into these generative models. So it's very rare that we will end up picking some run-of-the-mill generative model when trying to generate synthetic data for the setup at hand. So formally, the generative modeling problem can be formulated as follows. We have a set of real patient data. Let's say we have n instances for n patients. Each is represented with some variable x, so we have x1 up to xn. X can be anything, can be like a feature vector, can be time series, can be an image. And then the generative modeling problem is that we say that we have a real distribution P of x that captures the distribution from which this real data was drawn, and then we want to estimate P hat, which is an estimate of this distribution. And we don't just want to estimate the distribution. That's by itself is not very interesting, but we want to sample from this distribution. So whatever model that we will come up with needs to be able to handle high-dimensional data. So it should be easy to estimate. The generative model that we will build should be able to capture and estimate easily the high-dimensional data. And by that, I mean computationally and statistically. And it should be easy to train. So we'll probably not just use some vanilla maximum likelihood approach. The model that we'll come up with will be trained somehow, and we want it to be easy to train. And we should be able to easily sample from this model. So if sampling from the model is a computationally complex process and we want to generate like 1 million synthetic samples, that would be a hassle. So we want a model to estimate this high-dimensional distributions with an easy-to-train approach and that we can sample from. So the generative modeling literature usually builds on two different conceptual frameworks. The first is, of course, deep learning, where the focus is on learning rich, nonlinear representations with end-to-end scalable training using stochastic gradient descent, and where the models are very data-driven. We don't encode our prior assumptions in these models. And that's why deep learning is often used for modeling complex data like images, and is used for making predictions because we can learn these complex mappings from an input space to an output space. The probabilistic modeling literature is, on the other hand, usually uses simpler models, like simpler representations. Many of the constructions that we use in probabilistic modeling are encoding our prior assumptions, our prior intuitions on how a certain physical process works. And it uses principled inference approaches that need to be really handled on a case-by-case basis. So we don't just have sum loss function and gradient descent. We need to look on the likelihood of a model and then see whether the likelihood is tractable, like what kind of approximate inference approach we would use if the likelihood is not tractable, and so on. And the reason these two approaches are relevant in generative modeling is that we are modeling distributions. So it's really, by definition, a probabilistic problem, but we also want to capitalize on the power of deep learning. So let's look at probabilistic models. And let's look at a classical example of how a probabilistic model was often used to model clinical problems. So in a probabilistic model, as I said before, we really start by using our intuition to factorize a high-dimensional or a data distribution. It doesn't need to be high-dimensional. So there is a joint distribution of variables. Maybe you are looking at the time series data for a patient in a hospital or a patient who has a chronic disease, and we have follow-up data for his clinic visits. And then we make some assumptions about how this time series is structured in order to factorize the joint distribution of the data. So one common assumption is the Markovianity assumption. We can say that each observation at a time step doesn't depend on the previous observations. And we can assume that the patient's true health state is a latent variable that we don't observe. Here we're calling it ST. And then this health variable modulates some biomarker that we are measuring at the hospital or at the clinic, which we call XT. So this is a hidden Markov model. It's a classic example of a probabilistic model. It has been used a lot for modeling different types of healthcare data. And using a hidden Markov model, we can factorize the probability distribution of T observations over time, as shown in this slide. The next step is then we try to learn this model. So this is just the model specification. And then we look at the likelihood of this model. Usually when we have a latent variable model, the likelihood is not tractable because we are marginalizing on a latent variable distribution. So in HMMs or hidden Markov models, we use approximate inference. One very common approach is expectation maximization. And then once we learn this model, we can sample from it. So that's when we can actually generate synthetic data, synthetic time series patient data from such a model. We can sample hidden states, and then conditioned on a hidden state, we can sample a biomarker or observation, and then given the previous hidden state, we can sample a new hidden state, and so on. So this sequential sampling can be used to generate synthetic data. Now, HMMs are not classically used to generate synthetic data. They are just used to understand how a physical process evolves over time, but it's a generative model. We can use it to generate synthetic data. So why can't we just use probabilistic models? Like, why can't we look at each medical problem that we are dealing with and come up with some graphical model and some inference approach and sample from the graphical model? We can do this, but in many cases, we would need to have very strong assumptions. The graphical models or the distributions that the model specifications that we impose will have very limited representational capacity. And in many cases, we will have to resort to approximate inference that we will be tailoring to each case. So we will need to derive the likelihood of every problem that we are dealing with, see whether it's tractable, see like how to, what inference routine to use, and so on. So if you are dealing with medical data, for instance, and we are thinking of pixels as the random variables, how can we factorize this? There is no obvious way to do it. There is no intuition like we have in the hidden Markov model case, for instance. And even in the time series case, if we have electronic health record data, which is irregularly sampled and maybe not synchronized, and maybe very high dimensional with a lot of missingness, maybe we need to do some kind of representation learning to kind of learn the structure of the data in a data-driven way. So here comes the role of deep generative models, and these are data-driven models that are use the template learning approach, which is based on stochastic gradient descent and can learn complex representations. And the key idea of all the models I will discuss in the next slides is that we start with a simple distribution, maybe a Gaussian distribution, usually multivariate normal distribution. Then we pass it through a learnable representation F. And we learn this representation so that the output samples mimic the distribution of the real data. And the different deep generative modeling approaches will have different approaches on how to define this F and how to learn it. And the goal of such a generative model is to sample from it. We want to sample new data points from this model. We don't necessarily want to make predictions or anything like we are used to, but we want to sample new data points that are not in the real data. And that's what we would call synthetic data. So there are two very broad categories of deep generative models. The first is implicit likelihood models, and the second is explicit likelihood models. So in explicit likelihood models, we are able to write down the likelihood function. We are specifying a distribution for each variable in the model, and we can write the likelihood function. It might be intractable, but we can still write it. There's a well-defined likelihood function that can be deduced from the model structure and the model definition. And what an explicit likelihood model does is that it really fits a distribution. It's a density estimation kind of model. And there is another class of models that are that people call implicit likelihood models, and there we are not really specifying distributions on the different variables in the model. There is no clear likelihood expression that we can come up with to describe the model outputs. The model is really learning by comparison. It's doing a two-sample test, generating samples, comparing it with the real data, with some loss function, and then improving iteratively over its learning trajectory. So it's learning a distribution implicitly. It doesn't specify a distribution and tries to learn its parameters. It doesn't try to fit a distribution. It's kind of learning by comparison. It's more like a hypothesis test in that sense. This is just a depiction of how these two classes of models would look like. The first, the explicit likelihood model, have some distribution parameterized by theta tries to fit it. This can be a very complex distribution, but that's like the key idea of an explicit likelihood model. The implicit likelihood model generates synthetic samples, looks at these synthetic samples and compares with the real data with some loss function, and tries to optimize this loss function. So it looks a lot like a two-sample test in this case. So there are very different types of different instantiations of these implicit and explicit models. In the explicit models, we have models that optimize the exact likelihood function, and we have models that use approximate likelihood inference. And in the implicit likelihood models, there are models based on adversarial training and models based on method of moments. There are other kinds of models. This is in no way an exhaustive list, but we're just going to focus on these in this tutorial. Let's start with the explicit likelihood explicit approximate likelihood model. This is the variation autoencoder. So the variation autoencoder is really combining the deep learning philosophy with the probabilistic modeling philosophy. It's a latent variable model, and at the same time, it's an autoencoder. So it's a probabilistic spin-off of autoencoders that we can sample new data from. So how does it do so? So as I said before, every deep generative model is just a mapping from simple distribution that's data independent, like a noise distribution, to the data distribution. And in autoencoders, this mapping comes from an autoencoder. In variation autoencoders, this F comes from an autoencoder kind of architecture. So the way variation autoencoders work is that we have the input data X, and we are trying to probabilistically reconstruct this input data. So we have an encoder network that maps the input data to the noise distribution, or it's not noise, it's a latent space distribution, so the distribution of Z given X. And then we have a decoder network that maps Z to X. And if we model Z as a Gaussian distribution, then this decoder network will become our sampler. It will become our generative model that we can sample data from this Gaussian distribution independently of the real data, and then conditioned on the sample Z, we can come up with a new X, which will be sampled from the real data distribution. And this kind of model is implementing variation inference. So if we write the variation inference objective or the evidence lower bound for this model, it factorizes into like a model network and an inference network, an encoder and a decoder. And really the encoder is just used for training, but then once the model is trained, we can throw away the encoder and just use the decoder to sample new data points. And that's the synthetic data generation part that we care about. So variation autoencoders is one instantiation of deep generative models. This map from simple distribution to real data distribution is the decoder of an autoencoder architecture, and it's optimized using variation inference. A second class of models, of explicit likelihood models, that actually doesn't use approximate inference, doesn't use variation inference. It optimizes the exact likelihood, and it's one of the very few approaches out there that actually optimizes the exact likelihood and computes the exact likelihood, is normalizing flows. So in normalizing flows, we start with a noise distribution or a simple distribution P of Z. We map it to the real data distribution, and we select F so that it's an invertible transform. So that's the constraint that we put on F. So we choose F as a function that is invertible, and use the change of variable formula to optimize the distribution P of X, the distribution of the real data. So we know that change of variables formula is that if we apply a function to a random variable, we can evaluate the distribution of the transformed function using the derivative of the inverse transform and the distribution of the input variable. And for high dimensional data, we can do the same thing using the distribution of the input variable, which in our case would be just a multivariate normal, and the determinant of the Jacobian matrix of the transform. This approach can learn almost arbitrarily complex data distributions by composing flows. So by cascading different flows in stages, we'll still have a tractable likelihood because each stage is just a Jacobian of that stage and the input data distribution. And if we know the Jacobian of every stage, then we can still have a tractable likelihood expression, and we can learn very complex representation by this cascading or layering effect. So what makes a good or feasible normalizing flow model is two things. Like it's basically how we pick this transform F, how we pick this flow map. So we pick it so that the Jacobian transformation has an easy to compute determinant, and that the forward and inverse maps are easy to compute because this will affect how fast we sample from the model. And the Jacobian, the complexity of computing the Jacobian will affect the speed of training because the Jacobian expression is in the likelihood. So if it's hard to compute, then it's hard to optimize the likelihood. And as I said before, the key advantage of this model is that we can compute the exact likelihood, unlike all other models we discussed today. And this can be used to evaluate the model and also used for training with the exact likelihood instead of an approximate variation inference approach like in variational autoencoders. And the last approach that we'll talk about today is GANs. This is an implicit likelihood model that uses adversarial training, as I'm sure almost all of you are familiar with. So here, this transformation F is a player in a two-player game, a minimax game. So we have a generator network and a discriminator network. And the generator network is trained jointly with the discriminator network. So that the generator is trying to fake the discriminator by creating data that looks realistic enough, and the discriminator is trying to distinguish between real and fake data. And this minimax objective is used to train GANs. It's a bit of a unique philosophy for how to do generative modeling, but it's an implicit likelihood model because it involves the sample comparison. It keeps comparing the fake data with the real data, the synthetic data with the real data. So, of course, I didn't get into the details of each of these models. Each of them is worthy of a tutorial of its own. But as I said before, in most cases, you will not just pick a run-of-the-mill GANs or run-of-the-mill variational autoencoders or just vanilla normalizing flows for your application. We need to make design choices for the medical problem at hand. So if you are dealing with electronic health records or ICU data, maybe the mapping that we use in a normalizing flow or in a GANs model would be based on RNN. If we have imaging data, maybe we use convolutional neural networks. If we have comorbidity networks or drug-drug interactions or something that involves graphs, maybe we use some graph neural networks for constructing the representations within this normalizing flow model and within the GANs model or within the variational autoencoder model. So the second aspect of synthetic data generation that we will discuss is privacy requirements. So how do we define patient privacy, and how do we ensure that the generative models that we use to create synthetic data sets are respecting these privacy requirements? So even though the generative models that we would use to sample synthetic data sets are learning distributions and sampling brand new data points from these distributions that are distinct from the real data used to train these models can still overfit and can still memorize the real data points. So generative models still pose a risk of patient privacy violation because of memorization and overfitting. And we understand overfitting in the context of discriminative modeling. So in discriminative models, overfitting means that we have a model that has so many parameters that it actually perfectly fits the training data, but when presented with a testing data point, it may not generalize very well in terms of prediction accuracy on this the testing point. But in this context, we are not actually making predictions. So generalization shouldn't be defined as poor prediction accuracy on testing point. We are doing something that's conceptually very different. We are learning distributions. So in this context, memorization and overfitting are considered two distinct phenomena. And even though they don't have a single rigorous definition in the literature, you can think of them as follows. So memorization means that the generative model is covering some region in the support of the synthetic data just because of one outlier in the real data. So if you look at this figure on the left-hand side, we have this blue point is an outlier in the real data. The synthetic distribution is the dashed blue line. And the synthetic distribution is covering this entire region in the support just because it saw one training point at this region. Overfitting is literally means that the generative model is so overtrained that the distribution it induces is actually the histogram of the real data. It's concentrating all of its probability mass on the individual real data points. So when you sample from either of these models, the likelihood of seeing a real data point is higher than the actual probabilistic representation of this real data point in the real data distribution. So this is clearly a privacy violation. So if you have an outlier patient in a data set who has an interesting combination of clinical features, but there is no similar patients to that patient, and we have an overfitted generative model, the generative model can memorize the data for this patient and can keep showing it up in the synthetic samples. So how do we define privacy in this case? Like how do we, what kind of notion that we should use to evaluate model privacy or regularize the generative model so as to not violate patient privacy? Before defining privacy, we just need to make it clear that statistical inference is not a form of privacy violation. So sometimes people think that, or sometimes people conflate the inferences that we can make about individuals with privacy violations, and there are many media stories that confuse the two concepts. So in general, any statistical pattern in the data, any correlations in the data should be preserved, because that's the point from creating a synthetic data set in the first place. We want to have all the clinically meaningful relationships between variables be preserved in the data set without compromising the privacy of any individual who participated in the data set that we are fitting the generative model to. So for instance, if an analysis on the real data would reveal that a smoker has an elevated risk for lung cancer, if we have an individual patient who we know is a smoker and we predict that he has an elevated risk of cancer, that's not a violation of this patient's privacy. And even though that seems very straightforward and very clear, these concepts are often get confused. So we want to preserve all the statistical patterns in the data, especially the ones that are clinically meaningful and we are interested in, without having any patient's privacy being violated. So what does this really mean? So the notion of privacy is formulated through differential privacy. That's the most common definition of privacy, a mathematical definition of privacy, and the most prevalent one. So the differential privacy transcends generative modeling. It's a general definition that can be applied to any randomized mechanism. So if we have any randomized mechanism that produces an output y based on an input x, this mechanism is absolutely differentially private if all neighboring inputs to x and for all sets of outputs that are subset of the output space y, the probability of the mechanism giving the same changing the output based on the neighboring input data set is very small. So this means that if we have a study on the effect of a certain treatment on a population, the participation of any individual patient shouldn't change the overall conclusion of the study. It's a form of robustness. And in the generative modeling context, this may mean that we don't want the generative model to place a very high probability mass on any subset of the input data space just because one real training point is included in the training data set. So a differentially private algorithm is not especially sensitive to any individual data point, and this concept in the real world is very powerful because it means that if a patient is concerned about participating in a study, having his data collected because he worries about privacy violation and because he thinks that the output of the study may have an impact on him individually. For instance, the effect of like insurance premiums, an effect on clinical practice and how treatments are administered to different subgroups of patients and so on. If we know that the analysis that is based on this data set is differentially private, we are sure that any individual patient's participation shouldn't affect the outcome of the analysis. So each patient wouldn't have an incentive to not share his data with whatever clinical institution is collecting the data. So how is differential privacy incorporated into deep learning models in general, and generative models included? There are three different approaches. All are based on adding noise. So we can either add noise to the model outputs, we can add noise to the model parameters, or to the model gradients. And in the next part of the tutorial, Mihaela will show some examples of how differential privacy can be incorporated in the synthetic data generation mechanisms.
In this part of the tutorial, we are going to discuss generative models for synthetic tabular data. In the earlier part of the tutorial, Ahmed has introduced a taxonomy of deep generative models, and we have divided generative models into explicit likelihood and implicit likelihood models. An especially popular way to generate synthetic tabular data using implicit likelihood models is based on GANs. But before I'm going to discuss several ways to generate synthetic tabular data using GANs, I would like to introduce a more general recipe for generating synthetic healthcare data. And we are going to use this recipe throughout the remainder of this tutorial. In the first step, we decide the generative modeling approach to use. In this case, we are going to use GANs. In the second step, we are constructing an appropriate representation for the type of healthcare data under considerations. Initially, we are going to focus on tabular data, and we are going to use neural networks. In the third step, we are going to select a desirable notion of privacy to fulfill. And we can use different notions of privacy, as I'm going to show, both differential privacy as well as other notions. We are going to start with a different notion. We are going to generate tabular synthetic data that is capable to fulfill GDPR privacy requirements. And we call this framework ADS-GAN, which stands for anonymization through data synthesis using GANs. ADS-GAN is able to generate tabular synthetic data that closely approximates the joint distribution of variables in an original clinical dataset, thereby providing a readily accessible, legally and ethically appropriate solution to support more open data sharing under GDPR regulation. As I mentioned in the beginning of this tutorial, in order to mitigate the legal and ethical risk of sharing sensitive information, the identification or anonymization of patient records is commonly used. However, previous work has shown that the identification or anonymization is often not sufficient to avoid re-identification due to linkage through other identifiable datasets. Moreover, and this is an important point, neither GDPR nor HIPAA provide clear guidance on how to do anonymization to fulfill their regulatory framework. There is no clear mathematical formalism of these requirements. So in this work, we provide such a mathematical formalism and use it to generate synthetic data that is fulfilling GDPR regulations. Before I'm going to discuss the details of this, I'd like to highlight that generating synthetic tabular data, synthetic patient records based on real patient records is tricky. And the reason this is challenging is because generating such realistic synthetic data from complex patient records that are high-dimensional and come from complex distributions is hard. Moreover, it's important to note that often there will be a relatively small number of unique observations. For example, patients which may have a rare disease or who are outliers. And hence, it is hard to accurately estimate the complex high-dimensional distribution of this data without replicating the individual, and hence violating privacy requirements. So in order to deal with this complicated dynamic around anonymizing and sharing routinely collected healthcare data, we decided to address the problem in a new way. Instead of defining personal data of risk, which have both so far been unclear, we decided to formally, mathematically define a new notion of identifiability according to GDPR regulation. And we call this epsilon identifiability, and we introduce an identifiability metric. On the basis of this, we can then develop models to create synthetic data of individuals that are fictitious and yet could be drawn from the same population as the real data. So they conserve the characteristics and properties of the real data set. And with this model, the user can then define the threshold of acceptable identifiability. So this allows the model operator of ADS-GAN to weigh the risk-benefit ratio for any given problem when generating a synthetic data set. So they can weigh on one hand the risk of identification and re-identification versus the quality of the generated synthetic data set. So as I mentioned, we have formally defined a new identifiability metric, and this is shown formally in here, and this is the epsilon identifiability, which means that for each observation in the original data set D, defined as the probability that the distance to the closest synthetic observation is closer, in other words, not different enough, than the distance from the closest real observation, and that this is less than epsilon. In other words, we have 1 minus epsilon being the proportion of patients that are not identifiable by synthetic observations because the synthetic patient observations are different enough from the real patient observations. 0 identifiability represents perfectly non-identifiable data, and 1 identifiability represents perfectly identifiable data set. And again, epsilon will allow us to do such a trade-off between risk and benefit. We have then used ADS-GAN to allow us to move away from differential privacy, which we show in our work that at times may lead to generating synthetic data sets that are not having a very high fidelity, and replace differential privacy with a notion that still fulfills GDPR requirements based on the probability of identification given the combination of all data on any individual patient. How can we then train the GAN model to generate synthetic tabular data that fulfills such GDPR privacy requirements? Unlike a conditional GAN, where the predetermined variable set on which the GAN is conditioning is determined a priori, ADS-GAN learns to optimize a conditioning set per patient and generates all the components based on this. So let us now delve in a little bit more details to understand how ADS-GAN is working. ADS-GAN implements the generating function using a multi-layer perceptron. In more details, we first use the min-max scalar to normalize the continuous variables in the tabular dataset to 0, 1, and apply one-hot encoding to the categorical variables such that all the variables we have in the healthcare dataset are in the 0, 1 range. Then we concatenate the normalized continuous variables and the one-hot encoded categorical variables and put them in the input layer of the perceptron. At the output layer of the perceptron, we divide the continuous variables and categorical variables and use a sigmoid activation to the continuous variables and a softmax activation to the categorical variables, such that we can conserve the property of the continuous and categorical variables. Finally, we renormalize the continuous variables and reverse the one-hot encoded data to the categorical data to make the synthetic data the same format as the original data. How does the discriminator of ADS-GAN operate? The discriminator is trained to measure the Wasserstein distance between the joint distribution of the generated observation and the real observations. And the maximum value of the loss is the Wasserstein distance between the original and synthetic data distributions. And therefore, the role of the discriminator is to measure such a Wasserstein distance between the original data distribution and the synthetic data distribution. And thus, a large loss means that the difference in the joint distribution between the original and synthetic data is large. Therefore, we also call this the distribution loss. And we implement the discriminator function using a multilayer perceptron. But this is not enough, because while this distribution loss is able to optimize the accuracy of the data and the joint distribution between the original and synthetic data, it does not guarantee that the identifiability constraints, the GDPR constraints, are satisfied. To ensure that the generated samples indeed satisfy such identifiability constraint, we need to add an identifiability loss. And this represents the generator's effort to maximize the weighted Euclidean distance between the generated samples and the conditioned original samples, given that the generated samples are different enough from the original samples. We then train the ADS-GAN in the conventional way using an adversarial framework. An advantage of ADS-GAN is that it can improve the quality of synthetic data as opposed to other frameworks based on GANs, while ensuring that no feature combination could readily reveal a patient's identity and fulfills GDPR privacy requirements. Let us now look at another way of generating tabular synthetic data using GANs. But this time, we are going to select a different notion of privacy, differential privacy. So we would want to combine the differential privacy notion with the GAN framework. And we need to think about how to build such generative models that are differentially private. To do so, we need some background material. And this is the PATE framework, which stands for Private Aggregation of Teacher Ensembles. I'd like to note that PATE is constructing differentially private discriminative models, not generative models, which is what we need. But we need to start with PATE in order to understand how to make differentially private generative models. So let's see first, step by step, how the PATE framework works. In PATE, we start by partitioning the private data set in subsets of data, which are disjoint subsets. For instance, if a particular patient's record, Jane Smith's record, was in our private data set, then it is included in one of the subsets only. We train a machine learning model called a teacher on each of these subsets. There are no constraints on how the teachers are trained. We can use any machine learning model we like. All of the teachers solve the same machine learning task, but they are trained independently. So only one of the teachers has analyzed Jane Smith's record during training. This is the key idea underlying PATE. And the PATE framework tries to reduce the impact of one person, in this case, Jane Smith's record, to the output of the discriminative model. So we now have an ensemble of teacher models that were trained independently, but without any guarantees in terms of privacy. In the PATE framework, we add noise while aggregating the predictions made individually by each teacher to form a single common prediction. More specifically, we count the number of teachers who voted for each class and then perturb that count by adding random noise sampled from the Laplacian or Gaussian distributions. If most of the teachers agreed on the same class, adding noise to the vote counts will not change the fact that this class received the most votes. And in this figure here, we are portraying a setting where consensus among teachers is high. Therefore, adding random noise to the vote counts does not change the candidate label. On the other hand, when two output classes receive an equal or quasi-equal number of votes from the teachers, the noise will ensure that the class with the most number of votes will be the one of these two classes chosen at random. This provides correctness and privacy to the predictions made by the noisy aggregation mechanism. The student model is the final product of PATE. The student model is differentially private, constructed by this PATE framework. The student is trained by transferring knowledge acquired by the teacher ensemble in a privacy-preserving way. The noisy aggregation mechanism is a crucial tool for this. The student selects inputs from a set of unlabeled public data and puts these inputs to the teacher ensemble to have them labeled. The noisy aggregation mechanism then responds with private labels, and the student model uses them to train. What I'm showing here is the formal framework of the PATE framework, where TI is the teacher and NJ is the count of votes for each class. PATE lambda is the noise aggregation procedure, and with the Laplace random variables, we can achieve 1 over lambda differentially private predictive models through the PATE framework. Now we have a procedure to make differentially private models, discriminative models using PATE. Also, we have generative adversarial networks, but we need to combine both in order to create differentially private generative adversarial networks. And we call this framework PATE-GAN. We introduced PATE-GAN in ICLR 2018. And in order to be able to develop PATE-GAN, we utilize the post-processing theorem. Therefore, the only thing that we need to do is make our discriminator differentially private. This is the training procedure of the teacher discriminators. The generator takes random noise as input to generate synthetic data, and teacher discriminators are then trained to minimize the classification loss when classifying samples as real samples or generated samples. Note that we divide the entire data into the partitions, and each teacher discriminator only utilizes the subset of the data during training. Until now, we have no privacy guarantees. The key block is the generator and the student discriminator. To make the student discriminator differentially private, the generated labels from the teachers are aggregated with noise. The student discriminator utilizes the noisy aggregated labels to train the model. Following the PATE framework, we can construct the differentially private student discriminator, which is the discriminative model. Finally, the student discriminator loss is used to train the generator and make the generator differentially private. This is the comprehensive diagram of our PATE-GAN framework. To contrast this, I would like to highlight here a block diagram of another GAN framework used for generating synthetic data. This is called DP-GAN. Instead of using PATE-GAN framework in DP-GAN to guarantee differential privacy of the generator with the post-processing theorem, noise is added to the gradient of the discriminator during training to create a differentially private discriminator. Then, it also utilizes the differentially private discriminator to train the differentially private generator. It is always challenging to evaluate generative models because there is no ground truth to compare. So therefore, we propose some important and interesting evaluation procedures for synthetic data generations of tabular data. As we know, the main objective of generating synthetic data is to utilize this data for constructing predictive models. In this case, the synthetic data should preserve the original relationships between the features and the labels. We call this predictivity, and this can be qualitatively measured in 3 different ways. In the first setting, we just train the predictive model with real data and also test on real data. This is the standard supervised learning setting. In setting B, we train the predictive model with synthetic data and test on real data. This can evaluate how the synthetic data preserves the original feature label relationships. Setting C is more interesting. If we do not have any real data, we need to do hyperparameter optimization and find the best model only with the synthetic data. In setting C, we can evaluate whether synthetic data preserves the ranking of the predictive models on the real data. So we are going to train on the synthetic data and test on the synthetic data, rank the models, and then see if this ranking is preserved on real data. We use 6 different clinical data sets and other types of data sets to verify the superiority of the proposed method, our PATEGAN, and highlight the, how synthetic data generation with privacy guarantees can be determined. 2 of the data sets are private medical data sets called MAGIC and UNOS. All data sets are tabular data with various different number of samples and dimensions, and the area under receiver operating curve and the precision recall are reported in the tables of setting A. So what you see here is setting A, where we are training and testing using supervised learning on real data. Let us now move to the setting B. These results show the performance in setting when we train the model using synthetic data and test on real data. The baseline we use is DP-GAN. We also add GAN as another baseline, but note that this does not provide any privacy guarantees. As you can see in this table with different models, PATEGAN achieves the best performance, followed by DP-GAN. This means that the generated samples by PATEGAN preserve the feature label relationship of the real data better than DP-GAN. We also repeat the same experiments on setting B across 6 different data sets with different characteristics. And as you can see in these results, indeed, PATEGAN consistently outperforms DP-GAN with the same privacy guarantees. This means that the PATEGAN generated synthetic data is more realistic. As I explained earlier, differential privacy has a privacy budget. Here we change our privacy budget, epsilon, between 0.01 and 100. Higher the epsilon means the less private data. As you can see in this picture, there is a clear trade-off between privacy preservation and synthetic data fidelity or quality. This is somewhat trivial because to reduce the privacy budget, in other words, to create strong privacy preservation, we need to add more noise for label aggregation in the PATE framework, which makes the label for student discriminator more noisy. Therefore, the generator training would be also noisy and the corresponding synthetic data is less realistic. But what you can see here is that PATEGAN does a better job than DP-GAN. Lastly, we provide the results in setting C, where we train the model using synthetic data and also test on the synthetic data. We then rank the models on the basis of the synthetic data and compare this with the ranked models on real data. We propose a novel metric for that called Synthetic Ranking Agreement, or for short SRA, which has a similar concept as the well-known kappa statistic. If SRA equals to 1, it means that the ranking of the models in setting C is the same with the ranking of the models in setting A. This is important because it shows that we can do hyperparameter tuning and model selection only with synthetic data, select a model then based on synthetic data, and use that selected model to use on real data. You can also see here that PATEGAN outperforms DP-GAN with this metric as well, which shows that PATEGAN consistently generates high-quality synthetic data with privacy guarantees. Let us now look at another setting. We are going to use again GANs, but we are going to focus on the setting where we are trying to learn from one population and transfer what we have learned from one population to a new population that has different characteristics. We are not going in this case to consider any privacy notion. And this is important. For instance, in our work last year, together with NHS Digital here in the UK, we generated a variety of analytics to empower clinicians and medical personnel better fight this pandemic. But early in the pandemic, only a few of the hospitals were having high quality COVID data to learn from. Yet we wanted to learn from the data that was available in these hospitals for the sake of other hospitals across England. Yet these different hospitals had different characteristics, and the populations that they were admitting were different as well. And this is very important. As you can see in this intensive care medicine paper shown here, which is based on the NHS digital data, we show that there have been large differences in COVID-19 mortality across the different centers in England. And the reason behind that is that some of the centers have learned very fast how to deal with COVID patients, and other centers lag behind. So what we want to do is we want to learn how one particular center effectively is dealing with the COVID population and transfer this knowledge and this analytics to the other hospitals throughout England, while being mindful of the differences between these different centers. So what we need to do is we need to learn across jurisdictions in the presence of distribution mismatch, where the data does not come from the same distribution as the target data. So we learn from one hospital with one patient distribution for another hospital with another patient distribution. And also we have feature mismatch, because the data collected at different hospitals may be different as well. Some hospitals may collect certain data samples, some may not. In order to learn in the presence of such a setting, we have developed in iClear 2019 radial GAN. And radial GAN uses multiple GAN architectures to translate the data from one data set, one setting, to another. So we use these multiple GAN architectures to deal with distribution mismatch, and the adversarial framework is able to do that by ensuring that the translation across the different data sets respects the target distribution, and also by introducing a latent space through which all samples are mapped, we can deal with feature mismatch. So in this way, radial GAN provides a method for synthetic data generation of tabular data that can deal with distribution mismatch and feature mismatch. And in this way, we can create a synthetic data that can be used by the diverse hospitals that are dealing with diverse population that suffers from a particular disease, in this case, COVID-19. And what you can see here is the original evaluation of radial GAN, where we have used a magic data set that contains data across a variety of countries and a variety of studies, many studies, 216. And what you see is that the radial GAN framework is capable to generate synthetic data that is capable to deal with this type of distributional mismatches and feature mismatches much more effectively than other GAN frameworks such as star GAN or cycle GAN. Also, this is better than just using simple transfer learning. In this part of the tutorial, we are going to consider generative models for synthetic time series data. So what is a good generative model for time series data? The temporal setting poses some unique challenges to generative modeling that we have not considered when talking about generating synthetic tabular data. A model is not only tasked with capturing the distribution of features within each time point, but it should also capture the potentially complex dynamics of those variables across time. Specifically, in modeling multivariate sequential data, we wish to actively and accurately capture the conditional distributions of temporal transitions as well. There have been two main classes of approaches for time series generation: autoregressive models and recurrent generative models. A great deal of work has focused on improving the temporal dynamics of autoregressive models for sequence prediction. This primarily tackled the problem of compounding errors during multi-step sampling, introducing various training time modifications to more accurately reflect testing time conditions. And autoregressive models explicitly factor the distribution of sequences into a product of conditionals. However, while useful in the context of forecasting, these autoregressive approaches are fundamentally deterministic, and they are not truly generative in the sense that new sequences can be randomly sampled from them without external conditioning. On the other hand, a different line of work has focused on using generative adversarial networks for sequential data. And this was done primarily by instantiating recurrent networks for the roles of generator and discriminator. While straightforward, the adversarial objective seeks to model the joint data distribution directly without leveraging the autoregressive prior. Importantly, simply summing up the standard GAN loss over sequences of vectors may not be sufficient in many settings to ensure that the dynamics of the networks efficiently capture stepwise dependencies that may be present in the longitudinal time series data. So what we are going to do next, we are going to return to our recipe, our general recipe for generating synthetic healthcare data. And in step 1, we are going again to select GANs, but now in step 2, we are going to focus not on static tabular data, but rather on time series data. So we are going to focus on RNN representations. We are not going to consider explicitly any notion of privacy. So let us formalize this problem a little better. So let's consider the general data setting where each instance consists of two elements: static features and temporal features. So we are going to have tuples consisting of both. And we are going to consider that these tuples have some joint distribution P. The length T of each sequence is also a random variable, and the distribution of which we can absorb into P. So the desiderata now and the goal will be to ensure that given the available training data, we learn a density P hat that best approximates P. And we need to do so while fulfilling the following desiderata for the synthetic data generation: fidelity, the fact that the samples should be indistinguishable from the real data; diversity, that the samples should be distributed in such a way that they cover real data; predictivity, the samples should be just as useful as the real data when used for the same predictive purpose. For instance, as we shown before, train on synthetic data and test on real data. So our goal will be to use the training data D to learn a density P hat that best approximates P. And this is the high-level objective. And depending on the length, dimensionality, and distribution of the data, it may be difficult to optimize a standard GAN framework. Therefore, we additionally make use of the autoregressive decomposition of the joint P to focus specifically on the conditionals, yielding the complementary and simpler objective of learning a density P hat that best approximates P. So in this way, we are going to break the sequence level objective, which is aiming at matching the joint distribution, into a series of stepwise objectives that are focused on matching the conditionals. So in this way, we have a twofold objective. The first is global, and the second is local. Under an ideal discriminator in the GAN framework, the former objective takes the form of the Jensen-Shannon divergence, and using the original data for supervision via, for instance, a maximum likelihood training, the later takes the form of the KL divergence. Note that minimizing the former objective relies on the presence of a perfect adversary, which may not have access to, while minimizing the later only depends on the presence of the ground truth sequences, which we do have access to. So based on this insight, we have developed TimeGAN, which is natural framework for generating realistic time series data across various domains in the longitudinal setting. And this work was published in NeurIPS 2019. First, in addition to the unsupervised adversarial loss on both real and synthetic data sequences, we introduce a stepwise supervised loss using the original data as supervision. In this way, we explicitly encourage the model to capture the stepwise conditional distributions in the data. And this will take advantage of the fact that there is more information in the training data than simply whether the data is real or synthetic. And we can expressively learn from the transition probabilities and the transition dynamics from real sequences. Then we introduce an embedding network. So we are going to consider now this setting that is shown in here, where we are going to introduce this embedding network to provide a reversible mapping between the features and latent representations, thereby reducing the high dimensionality of the adversarial learning space. And this will allow us to capitalize on the fact that the temporal dynamics of even complex systems are often driven by fewer lower dimensional factors of variation. And it is important to note here that the supervised loss is minimized by jointly training both the embedding and the generator networks, such that the latent space not only serves to promote parameter efficiency, it is specifically conditioned to facilitate the generator in learning temporal relationships as well. Yeah. Then we are going to iterate, so the generator receives sequences of embeddings of actual data to generate the next latent vector. So this provides a framework to handle time series synthetic data, and we really generalize this framework to handle mixed data setting where we have both static and time series data that are generated at the same time. And this is the first framework to combine the flexibility of the unsupervised GAN framework with the control afforded by supervised training as used in autoregressive models. We have shown the versatility of this framework in a variety of real-world and synthetic data experiments. So we compare TimeGAN with several other GAN approaches, RC-GAN and CRNN-GAN, which are two of the most closely related works. And for purely autoregressive models, we compare against RNN trained with teacher forcing, as well as professor forcing. And for additional comparisons, we also consider the performance of WaveNet as well as GAN counterpart, which is WaveGAN. And to assess the quality of the generated data, we are again focusing on the three desiderata that we discussed before. We start with fidelity. And again, fidelity means that the samples should be indistinguishable from the real data. So for that, we are going to focus, as shown in here, on discriminative scores. And for a quantitative measure of similarity, we train a post-Hoff time series model to distinguish between sequences from the original and the generated data. And first, each original sequence is labeled real, and each generated sequence is labeled not real. And an off-the-shelf RNN classifier is trained to distinguish between the two classes as a standard supervised task. And we report, as shown in here, the classification error on the held out test set. And this is what you see in this setting. Then the second desiderata was related to diversity, and the focus was to understand whether how the samples should be distributed to cover the real data. And you see here a visualization of this. And for this, we apply TISNE and PCA. And we analyze both the original and the synthetic data sets, flattening the temporal dimension. And this visualizes really how closely the distributions of the generated samples resembles that of the original in the two-dimensional space. And this is shown in here. Now, the final desiderata was related to predictivity, usefulness, where the samples should be as useful as the real data when used for some predictive purpose. For instance, we train on synthetic data and test on real data. So the sample data should inherit the predicted characteristics of the original. And for that, we expect the time gun to excel, especially in capturing conditional distributions over time. Therefore, using the synthetic data set, we train a post-hoc sequence prediction model to predict next step temporal vectors over each input sequence. And then we evaluate the training model on the original data set. And you can see here the performance.
So the next model for generating synthetic clinical time series data that we're going to discuss is a model that belongs more to the variational autoencoder kind of models. And the representation that it learns to map the latent space to the observed space is based on an attention mechanism. So as we said before, we're making all of these modeling choices through our recipe for generating synthetic healthcare data. And in this particular case, we look at variational autoencoder type models with representations that are based on an attention mechanism. So the rationale behind this model is actually very similar to the hidden Markov models that we discussed earlier. So whenever we look at clinical time series data, we think of the patient as having a hidden health state, a state that represents the patient's health that is evolving over time. This can be the stage of progression of a chronic disease, or it can be the severity of illness of a critical care patient admitted to the ICU. And this hidden state manifests through observations. It can be lab tests or biomarkers or any kind of observations that we are making. And we are actually interested in synthesizing these observations. So the model that we are discussing here is an attentive state space model. That's a model that combines the deep learning approach for learning complex representations with the structure of a probabilistic model. As we said before, in these kind of models, we need to handle inference or training and learning and inference in a case-by-case basis. We need to define the structure of the model and then see how can we conduct a learning and inference. And the advantage of this kind of models that have a probabilistic spin is that they are interpretable. So not only we can generate synthetic data from these models, but we can also understand the dynamics of each individual sample generated by the model. And we can inspect each individual sample and see whether it makes clinical sense or not. And we can also incorporate prior knowledge, domain knowledge, and structure into the model. Because we have this factorization of the random variables through a graphical model, as we discussed earlier. So the idea of this attentive state space model is that in order to capitalize on deep learning, on the deep learning component of it, which would be responsible for learning more complex, more rich representations, we want to model non-stationary and non-Markovian dynamics. So in standard hidden Markov models that we discussed earlier, each new observation depends on the current state, and the current state just depends on the previous state. And it doesn't depend on the history of the patient prior to the previous state. This is a very strong assumption. In many cases, what happened 5 time steps ago may be more relevant to what's going to happen in the next time step, more than what's happened in the previous time step. So most of the time series data that we see in EHR, in electronic health records, are clinical events. And the most recent event is not necessarily the most important in predicting the future. Maybe a combination of things that happened in the past is going to modulate the state transitions in the future. So these are very non-stationary, very context-dependent dynamics, and the attentive state space model tries to learn these complex dynamics. So given all the observations that we have seen in the past, it assigns different attention weights to the previous time steps to come up with transition probabilities to the future states of the patient. So as I said before, the generative model is in general a mapping from a latent space to the data space that we are trying to mimic the distribution of, to be as similar as possible to the real data distribution. But in each case, we need to construct the architecture of the model based on the kind of data at hand and the kind of scenarios that we want to simulate. So here we have the encoder-decoder architecture are basically a sequence-to-sequence attention models. So as you see in the upper figure, the observed data passes through an encoder, and the output of the decoder are attention weights. And then these attention weights combine the previous states to come up with transition probabilities for the next state. And the inference goes in a very similar way. So the inference network also have the same structure. It tries to infer the attention weights, and from the attention weights try to infer the latent states. And the optimization of the model, as always, is conducted with a variational lower bound on the model likelihood. So with this kind of model, if we generate, let's say, 1 million patients, data for 1 million patients, we can then, because it's very interpretable, we can look at and this data and try to understand it. So for instance, here we are generating synthetic data for cystic fibrosis patients. That's a respiratory disease. And what these figures say is that for each state, for each hidden state in the latent representation that the model is learning, not only we are generating synthetic data that looks realistic, we are also seeing the hidden states of the patients and learning the distribution of biomarkers at each state. So for instance, the FEV1 percentage predicted is a measure of lung function. So for different states, for different hidden states, we have different levels of lung function. We have different levels for the prevalence of different comorbidities. And also the transition probabilities are changing over time. So in the rightmost figure, we are plotting a heat map for the attention weights assigned to previous time steps at each time step. And for a Markovian model, this would be just an identity matrix. We are just assigning a weight of 1 to the previous time step. But in reality, that's not what happens. So as we observe more and more data over time for a single patient, the transition process becomes less Markovian. What happened in the past and combinations of clinical events that happened in the past would affect the progression of cystic fibrosis in a patient. So for instance, if a patient was diagnosed with diabetes 4 time steps ago, and now he has a certain biomarker that's elevated, this combination of events makes a third observation more relevant, and this affects the transition probability in a certain way. So not only we can generate synthetic data with such model, but we can also understand the data that we generated and see whether it makes clinical sense. And we can also sanitize the data in a post hoc fashion and just remove samples that we think doesn't make clinical sense. Another approach that is based on normalizing flows this time uses a very different type of transform. So as we said before, we have noise distribution, and we want to find a transform, a learnable map or a learnable representation or learnable transformation F that transforms this noise distribution to the data distribution. So one transformation that's very natural for time series data is the Fourier transform. So the Fourier flows is a generative model for time series data that uses the Fourier transform as the flow map in the normalizing flow context. And as I said before, in the normalizing flow model design, we care about one particular thing, which is making the Jacobian matrix of the transformation easy to compute, because this will make the training the model computationally feasible. And we also want the model to have an easy to compute forward and inverse mapping so that we can sample from it efficiently. So why is the Fourier transform useful? Again, this goes back to the main point that we made in the beginning of the tutorial. For each type of data, there will be an appropriate design for the model architecture. So in many cases, the clinical data that we deal with is irregularly sampled, has variable length. I'm talking about time series data, of course. So a natural way to find a common representation for this kind of sparse variable length data is transform it to a spectral domain that has a fixed number of frequency components. So that's what a Fourier transform does. It transforms the time domain signal to the frequency domain. And if there is a different sampling rates, if we have different lengths for different time series, we can pad the length difference with zeros and apply the Fourier transform. It can work with different sampling rates. So we can find a common representation for sparse and messy time series data using the Fourier transform. But that's not the key advantage of it in the context of normalizing flows. The key advantage is that the Jacobian of the Fourier transform is very easy to compute, and it has this convolution property that makes it especially relevant in many computational contexts. So if we apply pointwise multiplication in the frequency domain after transforming the signal, the data to the time series to the frequency domain, if we apply any filter to this data in the frequency domain, this will correspond to time domain convolution. So with in a very computationally efficient way, we can apply time domain convolution as our flow map. And this way, with a limited number of flow compositions, we can learn complex representations. So the architecture of this model goes as follows. We have the data, which is a set of time series with maybe different sampling rates, different lengths. We apply a fixed length Fourier transform to all data points, find a common spectral representation for these data points. And then we take the real part and the imaginary part separately. The real part is taken as is and is applied to a spectral filter that's data dependent, and it depends on the imaginary component. And this filtered signal is the output of the flow. And the inverse flow can be computed very efficiently using pointwise division and inverse Fourier transform. All of them can be done in linear arithmetic time. And what this entire transformation achieves is actually time domain convolution, a time-dependent time domain convolution, which can learn very complex representations. So to sum this part of the tutorial up, as we said before, there is a common recipe for generating synthetic data, but the specific modeling choices will depend on the kind of data that we are dealing with. There's a wide variety of data that we encounter in the clinical setting. If we have very high dimensional data that is well structured to some extent, so regularly sampled time series data in an ICU, maybe we just use where we measure maybe 30 or 40 biomarkers and lab tests. Maybe we just use the time GAN model. If we have a chronic disease where we have almost regular clinic visits for the patient, where we maybe have annual visits for the patient in which we collect a rather limited number of observations, then we can use a probabilistic model like the attentive state space model, where we also care about interpreting the disease progression in the synthetic data that we generate. If we have data that is irregular, have variable time, variable lengths, or data that has periodicity and is low dimensional, maybe we choose the Fourier flows. Each of these are instantiations of the general recipe that we presented upfront. So these are all transformations that take noise, transform it to the real data distribution, and we can sample from. But these different representations are appropriate for different kinds of data. So the last part of this tutorial is concerned with evaluating synthetic healthcare data. So let's say that we already follow the recipe that we described earlier. We already have a generative model from which we sampled a synthetic data set. How do we know if this synthetic data is of good quality? And what does quality really mean in this case? So one way to evaluate synthetic data is to bring a clinician or an expert to look at the data and see whether it looks realistic or not. And this may be useful when in imaging data, for instance. But that doesn't work in all cases and doesn't work for all data types. So we may have generated data for millions of patients, and it may be hospital data. So we generated time series data for patient stay in hospital for many days. So it's not feasible to bring somebody to sift through this, all of these generated synthetic variables. It's also sometimes hard to make sense of the data by just visual inspection and also see whether the real data distribution is being captured in the synthetic data distribution or not. Another pragmatic way to evaluate synthetic data is to train a predictive model on the synthetic data and test it on the real data. And this might be useful in a very limited sense, meaning in the sense where we actually just care about this predictive task, and that's why that's what we generated the synthetic data for. But we can have a predictive model that's trained on synthetic data, generalizes very well to the real data, but still we have poor quality synthetic data that has a lot of noise that's kind of ancillary or like tangential to the prediction task that we use to evaluate the synthetic data based on. So there is a need for coming up with metrics to evaluate generative models in general, and this applies beyond the clinical application that we are concerned with. Of course, going back to the discriminative models, it's very easy to evaluate predictive or discriminative models. We just leave out a fraction of the data, train the model on the training data, and test it on the test data. And we have ground truth labels that we can compare the predictions of the predictive model with, and then compute some kind of accuracy score, area under receiver operating characteristic curve, mean square error, and so on. In generative models, because generative models are not, or synthetic data are not task specific, and they are unsupervised, and there is no ground truth for each sample, whether it's good or bad. There is no obvious way to evaluate a generative model. So the existing scores for evaluating generative models can be categorized into two different categories. Some scores are very domain specific, like expert opinion, scores for, especially in the image synthesis domain, scores that are based on pre-trained representations on ImageNet, like Fichet inception distance. And the kind of model or domain agnostic scores are basically the model likelihood or statistical divergence, the distance between the real and the generative distributions. But of course, as we know and as we discussed earlier, there are two types of models: explicit likelihood models and implicit likelihood models. And implicit likelihood models do not have a computable likelihood, so we have to estimate it with methods that are computationally inefficient. And the likelihood itself, as we will discuss later, is not the best way to evaluate synthetic data or generative model for many reasons. One is that it doesn't evaluate the quality of individual samples, and we discuss later why this might be important, especially in the context of clinical data sharing and synthesizing. It's not always very interpretable, and doesn't really help us with diagnosing the different modes of failure of the model. So why, if the likelihood is bad, why is that? Like, is there a mode collapse that's happening, or is there a lot of noise generated by the generative model, or it's just a single number? It doesn't help us diagnose the different modes of failure that the generative model can go through. And it doesn't scale well with high dimensions. And there are plenty of examples available in the literature where we can have a generative distribution that's most of the time sampling from a noise distribution, but because the data is very high dimensional, the likelihood function is really not very sensitive to to the quality of the real data itself. As we discussed earlier, generative models are two types. There are implicit likelihood models and explicit likelihood models. And implicit likelihood models like GANs do not have actually a computable likelihood function, so we cannot use the likelihood to evaluate these models. And even explicit likelihood models like variational autoencoders and many others do not have tractable likelihood functions, so it's hard to even compute the likelihood for those. And the likelihood itself, even when available, is not really the best way to evaluate a synthetic data set for many reasons. One, it's being uninterpretable. So it's hard to look at the likelihood number and make sense of it and compare it across different settings, for instance. It's not useful for evaluating individual samples, and we'll discuss later why this might be useful. And it doesn't help us diagnose the different modes of failure for a generative model. So if a generative model has poor likelihood, it's hard to tell why is that. Is it missing some modes in the data? Is it inventing some modes? Is it generating a lot of noise? You cannot really look at the single likelihood number and kind of debug the model modes of failure from that. And it also doesn't scale well. It doesn't is not as sensitive to synthetic data quality for high-dimensional data sets. And there are many examples in the literature where you can construct scenarios where you sample data from a mixture of noise distributions and real data distribution and still get a great likelihood value, even if most of your samples are poor. And this happens especially in high-dimensional data sets. So the key takeaway from this discussion is that generative models fail in different ways, and there can be one number that describes the performance of generative models. So it's more useful to look at multidimensional metrics. And in the literature, there are 3 dimensions that people evaluate, 3 dimensions for model quality. The first is fidelity, which is a measure of how good the synthetic samples are, how realistic they are. The second aspect is diversity. So how much of the real data is actually covered by the model? Is the synthetic data diverse enough that it represents the variance in the real data? And generalization or memorization, which is how often does the model copy the training data? To what extent does the synthetic data, to what extent is the synthetic data really novel and is really a sample from the distribution of the real data and not a copy of an individual of specific real samples in the training data? And it would be useful for the sake of model diagnosis, for the sake of model comparison, to have probabilistic interpretable quantities as the performance metrics. So a number that we can look at and understand what it means and can compare across different data sets for different models. Something that's analogous to model accuracy or area under receiver operating characteristic curve in discriminative modeling. So people have proposed different metrics for generative models that are satisfying these criteria, precision and recall being the most prevalent ones. So precision is really a measure of the fraction of synthetic samples that look realistic. That's really the definition of fidelity. And recall is the fraction of real samples that that generative models can synthesize. And of course, we know precision and recall from classification analysis, but here they have a different meaning. They are really measures that compare the supports of the real and synthetic distributions. So as shown in this figure, we have the support of the synthetic data colored in red, the support of the real data colored in blue. Ideally, we would like these 2 supports to coincide. This would be a very nice synthetic data set. But if they don't coincide, then the samples that lie beyond the support of the real data are considered noise. They are not realistic samples. They have probability 0 under the real data generation process. And the samples that belong to the real data that lie beyond the support of the synthetic data are considered samples that are not covered by the generative models. And this is very important when evaluating the fairness, for instance, of a generative model. So if we synthesize data that has multiple races and multiple social classes, or is the model generating data for all of these patient subgroups, or is it just fixating on a certain race or a certain social class or certain or any kind of patient subgrouping? So a model that's covering all of the diversity and variations of the data would be a model with high recall, a model that's not going outside the support of the real data would be a model of high precision. And these numbers are just probabilities between 0 and 1. It's really the rate in which the model fails in these two different ways. Of course, the precision recall analysis is very useful, but also has its problems. So we can think of all kinds of scenarios where a generative model is just generating outliers or very low probability samples, but still covers the supports perfectly. So we can have arbitrarily different distributions on the same support. And this would still be a suboptimal generative model. We'd ideally like to copy the distribution of the real data in the synthetic data, because if we use the synthetic data to develop predictive models that we will deploy in real life, they would not generalize well if the real data distribution is not being mimicked in a synthetic data. It's also hard to detect mode collapse, mode invention, different modes of failure with these kind of metrics, because they really just compare the supports of the real and synthetic distributions. A more refined definition of precision and recall that we proposed is what we call alpha precision and beta recall. So instead of comparing the support of the real and synthetic distributions, we compare what we call the alpha support of the distributions. And this is the smallest support of the real distribution or synthetic distribution that contains alpha probability mass. And this would typically concentrate around the modes of the distributions. And then we compute the precision and recall for different values of alpha and obtain an entire precision and recall curve for different values of alpha. And these curves will be perfect only if the two distributions coincide. So this way we compare the supports of the real and synthetic data, but also compare the distributions at the same time, the real and synthetic distributions. And an optimal model would be a model that has precision 1, recall 1 for all values of alpha. It's also, the precision and recall analysis is also very useful when we want to make clinical sense of the data. So many clinicians that are involved in the synthetic data generation worry about the clinical meaning of individual samples generated by a synthetic model, whether certain samples can assume values that do not make clinical sense. And some people use rule-based approaches to kind of enforce some conditions to be satisfied in the synthetic data, or rule out samples that do not satisfy certain conditions. The precision recall analysis can be very useful to spot on unrealistic samples. So, for instance, if we have a very simple tabular data set with clinical variables, but one patient in the synthetic data is aged 120 and has systolic blood pressure 200. These are clearly non-realistic numbers, or wouldn't occur in the natural real data. So this will be a low precision sample and will be beyond the support of the real data. So the power of precision and recall analysis is that it doesn't just evaluate the generative model, but evaluates individual samples. We can sift through the synthetic samples generated by the model one by one and rule out the imprecise ones. We can also look at the real data samples one by one and see which of them are not covered by the generative model, and see whether there is a consistent feature that is not covered by the generative model. So for instance, patients with a certain chronic condition, or patients of a certain age, or patients of a certain race, and this can help us diagnose the modes of failure of the model in a more clinical sense rather than the modeling sense. The last thing that's very hard to evaluate is generalization or privacy. Most of the existing metrics are distance metrics that measure the distance between the synthetic data and the real data, and see whether, through basically a hypothesis test, see whether the synthetic data is too close than it should be to the real data. And this is a different definition than differential privacy. There's no way to measure differential privacy in a post hoc fashion on a sampled synthetic data set. But most existing metrics use these kind of distance measures. So, for instance, if you have an outlier patient with a very specific combination of clinical features, and you find this patient being consistently showing up in synthetic samples, this means that this patient is being copied in the synthetic data. This patient sample is being memorized. And the way you know this is that we use the nearest neighbor approach or computing the distance between each sample in synthetic data and real data, and see samples in the synthetic data that are exceptionally close to samples in the real data, in portions of the real data support that are not very dense, that doesn't have a lot of samples. So we shouldn't really have samples in the synthetic data that are exceptionally close to the real data when they are outliers. So there's not a lot of work done on evaluating privacy, as in coming up with metrics for the achieved privacy of a synthetic data, but most existing metrics evaluate memorization through distance metrics. So because of this sample level metrics that we have to evaluate generative models, we can add a fourth step to our recipe, which is sanitization. So if we have a generative model that is generating a very, very good samples, covers the real support, but also generating a lot of noise, we can remove the bad samples, the noisy samples, by looking at the precision metric on a sample level and removing samples that have low precision, or meaning the samples that are outside the support of the real data. So sample inspection with sample level metrics not only can evaluate generative models and can help us pick the right generative model for the problem at hand, or compare the performance of different generative models in synthesizing clinical data, it also can help improve the synthetic data for any given model by just sifting through the individual samples, spotting out the imprecise ones or the memorized ones, and removing them from the data set. So finally, this is the overall recipe for generating synthetic healthcare data. We decide the generative models to use, and we select the representation that best fits the data structure that we are dealing with. We try to incorporate differential privacy in the model, learning, or if that's possible. And then we evaluate individual samples generated by the model and remove the bad samples. And this can be a feedback loop to the first step. If using these samples, we find that some modeling choice is better than the other, maybe we go back and maybe GANs outperform normalizing flows based on this precision recall metric. So we pick GANs instead of normalizing flows. And then after that, we also remove the bad samples generated by GANs. And by bad, I mean memorized samples or samples that are not precise. And that's because we can evaluate individual samples using precision and recall metrics. So now I hand the presentation for Mihaela to discuss future directions.
We have now arrived at the final part of our tutorial, where we are going to briefly discuss future directions and several resources. We have discussed in this tutorial how to generate synthetic healthcare data in the static tabular setting and time series setting, but we can go beyond that. So we can generate synthetic multimodal data that combines high-dimensional genetic information, medical images, with time series data. And this is needed if we want to create synthetic data for complex environments such as electronic health records or clinical registries. Also in this tutorial, we mainly focused on generating time series data where data is sampled regularly, like for instance in a hospital or ICU. However, the next frontier is to come up with synthetic data generation and generative models for asynchronous, sparse follow-up clinic visits, where data may be informatively missing rather than missing at random. We also need to come up with new methods for evaluating synthetic data that go beyond the ones that we discuss here and may include fairness and bias in synthetic data. We also may need to develop new evaluation metrics for different domains and diseases, as well as relationship between various diseases, such as, for instance, comorbidities. Finally, we need to come up with environments where we can estimate and assess the performance of clinical decision-making from real observational data. For that, we have recently developed MedKit, which is a synthetic data engine for decision-making. And this is more than just synthetic data. It is a full testing suite for testing policies, for testing decision-making in a clinical setting. And this is important because in healthcare, we are having only limited batch data sets. So we need to be able to evaluate policies in a fully offline setting. We cannot do online learning and online reinforcement learning. We need to be able to rely on such synthetic environments to evaluate the performance of our clinical recommendations and clinical policies. And modern time series generation methods, such as the ones that we have discussed here, methods such as TimeGun, don't disentangle environment and policy. Hence, we cannot do this effectively. So MedKit is able to do that. The desiderata we addressed is we created a collection of realistic environment models with a variety of expressive and customizable policy models. In this way, MedKit is able to provide ground truth knowledge in complicated and realistic clinical settings, which is enabling us to test decision-making models and policies. Again, why is this important? Because without ground truth, policy inference in the clinical setting cannot be validated. We cannot interact with an environment directly online, like in a reinforcement learning setting. We need to learn again and estimate the quality of these policies in the clinical setting based on the offline data. And MedKit is providing us such an environment. So MedKit provides policies learned based on clinical behavior, but with customizable parameters. So users can alter ground truth structure, the Markovianity of the environment. We know that in many settings, the clinical settings are not Markovian, but rather semi-Markovian. Bounded rationality of decision makers can be evaluated, individual consistency, as well as we can simulate and emulate variation in practice. Or somebody can bring their own completely custom policies to MedKit. So this enables us to create a synthetic simulation environment for estimating and evaluating customizable clinical policies for inference. If you would like to see different resources beyond the ones that we have highlighted here, I invite you to take a look at our blog that describes our vision on how synthetic data can break the data logjam in machine learning for healthcare, thereby catalyzing a transformation in medicine and healthcare. If you want to see our own various works on synthetic data beyond what we have highlighted here, please take a look at our website dedicated to synthetic data work. And also, more importantly, if you would like to play with the various methods that we discuss here, I invite you to take a look at our GitHub, which contains software associated with all the various works that we discussed here. Finally, we have started around 1 year ago a set of engagement sessions dedicated to machine learning researchers, in particular students, but everyone is invited, where we are trying to understand what machine learning can do for healthcare. So if you are interested, please join our group, our engagement sessions by submitting your name and email address to this session. And join us in building an environment where machine learning models can flourish and can indeed revolutionize healthcare. Thank you very much.